Hello everyone, I am Shagun and I'll be presenting my project for the class Image Processing in Computer Vision, and my topic is Satellite Image Resolution and Contrast Enhancement using techniques like Wavelet Transform and Brightness Preserving Dynamic Histogram Equalization. This is the outline for my presentation. So first of all, I'll be going through a brief introduction and then what is satellite imagery. Then I'll go through with the terminology used and the proposal description of this project. I'll after that go through on the results that I have got and the evaluations that I have done based on these results, and then I'll be concluding my presentation. So starting with for the introduction, satellite imaging is a technique that is used in the fields of computer vision where we take unrefined images from the sensors or the cameras that are placed on the satellites and then we enhance them for extracting meaningful information. This is one of the leading trends on commercial mobile applications such as Google Maps, Google Earth, etc. It is an important phenomenon to provide us with useful information about topics such as agriculture, warfare, biodiversity, conservation, and meteorology. Remote sensing through these images help us to know many other factors like vegetation and forest cover, water distribution, Earth's atmosphere, etc. Let's see what is the problem at hand. The problem at hand deals with that these satellite images, they are taken from huge distances and in very unfavorable environments. So therefore, we need powerful algorithms for improving the resolution of these images. The image that works as the input to our system can be corrupted due to many reasons that can include bad focus or can be affected by noise. The other factors that cause the unfavorable environment include immense heat from sun, rotation of satellite camera, and the angle to which it is pointing with respect to the angle of Earth at that time. Therefore, powerful algorithms should be there in place so that these low resolution, low contrast images that are taken in these environments can be developed to high resolution and contrast enhanced images so that meaningful information is not lost. Wavelet transform is going to be the major technique used in this project. So first of all, what is wavelet transform? Wavelet transform decomposes signal into its basic mathematical functions that are called wavelets. These wavelets then distribute data into different frequency functions and then study each function component by attaching a resolution scale to it. The greatest advantage of wavelets is that they have the capability to split the image into very fine details. And they also have the ability to finely represent functions that have sharp peaks in them or have discontinuities, and therefore they can be able to represent with accurate reconstruction and deconstruction of signals. In my project, I am using three types of wavelet transforms: discrete wavelet transform (DWT), stationary wavelet transform (SWT), and inverse discrete wavelet transform (IDWT). And these are going to be discussed in the next sections. So first of all, DWT and SWT. Discrete wavelet transform is the type of transform where the wavelets are discretely sampled, and these discrete set of wavelets are expected to follow some predefined rules. In my project, DWT is used to decompose an input image into its respective subbands as shown in the figure above. So this input image can be divided into 4 frequency subbands. This is the low frequency, high-low, low-high, and high-high. Then I'm going to use stationary wavelet transform, which works similarly to the DWT, but in this project it acts as an intermediate layer required to enhance the image outputted from DWT. Then I'll be using inverse discrete wavelet transform, which is basically the inverse of the discrete wavelet transform, as it recombines all these subbands that are the result of the decomposition, and then they can be used for producing a high resolution, low contrast image. The next technique used in this project is interpolation. Interpolation is one of the major techniques used in the field of image processing, and it is used to produce high resolution images by enhancing their overall resolution quality. It can be defined as a phenomena to construct new and unique points of data lying within the existing range of discrete set of already known data points. And it helps us to find the values of a function at various positions that are lying among its samples. This project uses the technique of Laxos interpolation. The next technique is BPDHE and SVD. So now BPDHE stands for Brightness Preserving Dynamic Histogram Equalization, and it is used to set the contrast of digital image to appropriate levels so that no useful information is lost. It also smoothens the image and maintains its brightness. SVD, on the other hand, is another technique and stands for singular value decomposition, and it is used to enhance images having low contrast. So therefore, BPDHE takes images that are low on brightness and SVD takes on images that have low contrast. There are many advantages of using SVD, which is that the compression speed is very fast and it can identify the slightest changes in the input and produce a stable output matching with those changes. So now I'll be combining all the terminology that I've talked about and tell you how it works on the flowchart of my project. So first of all, a low contrast and low resolution image is given as the input to the system. Then it is decomposed using SWT and DWT, and we take the high frequency subbands, which are LH, HL and HH, and we interpolate them using Laxos interpolation and having a interpolating factor alpha. Alpha can be any number. Then with these interpolated images, I'm going to do an inverse discrete wavelet transform to combine all these subbands to produce a high resolution and low contrast image. This HRLC image will be given as input to my BPDHE, and then BPDHE would enhance its brightness and equalize the histogram. Then that image will be given to another DWT, which is gonna separate it into 4 subbands. For these 4 subbands, I'm just gonna use the LL subband and give it as an input to my SVD. My SVD will then calculate a new LL subband by a correlation coefficient. The last step performs IDWT to combine the new LL subband computed by SVD and the remaining high frequency subbands that we calculated, and this is gonna give us high resolution and contrast enhanced image that will be the final output of our system. These are the results that I have got by running my code. So I took a colored image, and then the second column of this presentation shows you the gray image, and then the third column shows you a high resolution and contrast enhanced image. I also did it by inputting a simple gray image, and again I was able to produce more bright and images that are high on resolution and have an enhanced contrast as compared to the inputs. I'm now gonna go over my code to show how I implemented this. So my major file is test.m, and other files are high resolution, contrast enhancement, interpolate image, BPDHE, and readings.m, which will be my helper functions for test.m. High resolution contrast enhancement basically is the file that is implementing my project into the MATLAB code. So first, as I said, that the input image, which is low resolution and low contrast, will be given to the DWT. So therefore, I have 4 subbands that are coming out of this DWT. I am using 9x7 wavelet filter, which is given by Bior 4.4. As I said, for these DWT, we are only concerned with the high frequency bands. So only the high frequency subbands are given as input to my SWT, and the LL subband is not given as an input. For my interpolation, I am using alpha equals to 2, and this can be any number. Then I am calculating my interpolated image for all these 4 subbands. using both TWT and SWT. This will give me an image which is high resolution and low contrast. And then I'm going to perform IDWT on them so that all these subbands are recombined together. Then I have performed BPDHE, and this calls to this function here, and the code for this function is here. This function, the BPDHE function, I took from a MATLAB file exchange, but all the rest of these files are made by me. So the BPDHE functions provides it with the brightness preserving dynamic histogram equalization code. Coming back here, so then once I have the BPDHE, I am again going to perform a DWT, and this time I am only concerned with the low frequency band, LL band, and I am providing it to SVD as my input. The correlation coefficient of the SVD is calculated like this, where I am dividing maximum of high resolution low contrast upon maximum of low resolution low contrast. My final image is gonna be the LL that I got from SVD and the other high frequency subbands calculated from the previous IDWT. Interpolate image is just a helper function where I'm going to use Langsos's interpolation, as I said, for the technique of interpolating my images here. So now I'm going to run my code. The input to this is right now 1.jpg and the outputs should be two. One is the rectified output and one is the grayscale image output. So once I run this code, this is the output image that I get, which is high on contrast and high on enhancement too. I'm going to prove this with quantitative results in my presentation here. So the analysis for it shows that I have compared them on two bases. One is MSE and the second one is PSNR. For MSE stands for mean square error and PSNR stands for peak signal to noise ratio. So these two values are the ones that I have compared. I have compared them for these four images: HRCE _1, _2, _3, _4. HRCE stands for high resolution contrast enhanced image. So I would like to go back to my results. So here on this slide I have two images, and then on the next slide I have two images. And for these four images, I have calculated my results. I would like to tell what is MSE. So MSE is the mean square error and PSNR is the peak signal to noise ratio. For an image, the lower the MSE, the lesser is the noise. On the other hand, a higher value of PSNR means a better quality of the enhanced image. The values in these tables adhere to these trends, showing that the output images are the optimal ones. So for all these images, I have my MSE as low as 1.5 and my PSNR as high as 46.36 and 46.37. Now I would like to conclude, and on conclusion I would like to tell that this project gives you a new method of developing high resolution and contrast enhanced satellite images using wavelet transform, and these procedures can be done on any image to produce a high resolution image. So the code built was run on 4 sets of images and enhanced images were received at the output, and the quantitative measures show the validity of the proposed method. But there is a small security issue with deploying all these high resolution satellite images on the World Wide Web, because there have been studies where all this information was provided by Google Earth and they can be used by terrorists or attackers with malicious intent. Hence, methods to improve privacy are one of the major concerns in the subject of satellite imaging. For the successful completion of my project, I would like to thank Dr. Wu for his knowledgeable guidelines and very extreme developed lecture notes. And therefore, I would just like to conclude my project here. Thank you so much for watching.